This video is going to look at one of the many applications that you see with exponential functions and looking at the models that you can create and the relationships that happen. And we're going to look at doubling and half-life. So doubling, to give you an overall view of that, is the amount of time that it takes for some initial amount to double, which makes it times by 2 in size. And it doesn't really matter what the starting value is. So if you had 100, it would double to 200. If you had, 57, it would double to 114. But it's the time it takes for it to double. And again, it's really irrelevant as to how much you start with if what you're looking for is time. Half-life will be what it says it is, half of the life of whatever it is that you're looking at. And a lot of times that's substances, like radioactive substances, have a half-life. If you're looking for the amount of time that it takes for however much of it you started with to decay to half of what it was. So like if you had 100 grams, how long would it take to get to 50 grams? Or, whatever the unit is for that substance. Again, it just depends on what it is. But it's how long it takes to be half of that left, hence the word, and calling it half-life. So the capital letters Q and P are used a lot in the textbook for this section. Q is used a lot with the exponential function anyway, and P is used a lot for population. Both of those have an exponential growth or decay. So the P and Q, if they're used for values, they're going to use these Q and P with a little subscript of 0, and it's read Q naught or P naught to indicate a starting value when time is 0. So that is indicative of that initial value, that A that we've used before, but you may see a little P naught or a Q naught, and all that's representing is initial value. So I wrote these two equations here at the bottom. This P equals P naught times e to the kt power. That's just, indicating that you have some population equals some initial population, and this one happens to have a continuous growth or decay rate. The Q function is just your non-continuous, so whatever your value is, it's your initial value times some growth factor to a power. I mean, we've had these exponential functions before. It's just now I wanted to present them to you with the P naught and the Q naught notation, because if you look at doubling, then what you actually do is you take the initial population and you double it, which is just times in by 2. So if you're looking for the time it takes to double, the setup will be, I want to double the initial population, given my initial population, with e to the kt power. And algebraically, if you watch and see what happens here, that initial population divides away to 1, and what you're left with is 2 equals e to the kt power. So if you know the continuous rate at which it grows or decays, then you'll be able to find the time that made that value double, and then you'll end up solving this for t, because you'll be given the k value. And the same thing for the non-continuous equation. If you wanted to double that one, it would double the initial value equals the initial value b to the t power. The Q naught values cancel, and you're left with 2 equals a factor to a power, and then you're going to use that and solve it for the power using logarithms. Okay? If you wanted to do half-life, which ran out of room on the bottom of this one, I might erase this. For half-life, it's a really similar setup, but instead of doubling the initial value, you're going to half the initial value equals initial value e to the kt. Again, the P naught variable divides to 1, and you're just left with 1/2 equals e to the kt. Or on the other equation, if you half the initial value Q, the Q initial values cancel, and you're left with 1/2 equals a growth factor to a power. And in either case, you're going to solve for the time that it takes for that half to exist. Okay, so that's the algebra that's going to happen with a lot of these, and the setup is that you can do this doubling equation or the halving equation on the initial value, and it is completely irrelevant as to what that starting value is if you're looking for it to exactly double or to be half there. Okay, so a few examples on these. Question, how long will it take to double an investment in a bank account that grows at 2.7% per year? All right, so for this question, you don't have the word continuous, so this is not continuous growth. So make sure you understand that when you set the equation up. So it's growing, okay? So we're going to use the regular exponential, or AB to the t, however you want to think about it, in that we don't really know the initial value, right? But we know that it's growing at 2.7% per year. And when we've dealt with growth rates of 2.7% per year, 2.7% is 0.027 as a decimal form. And in order to turn that into a growth rate, we make that 1.027. And we'll raise that to the t power. Okay? So if we want to find out how long it takes to double, the setup will be, we'll double the initial value equals whatever the initial value was times the 1.027 to the t power. The initial values divide away to 1. You're left with 2 equals 1.027 to the t power. And now we are set to solve this exponential equation for t. The base is not e, so I would prefer to just do a regular logarithm, not a natural logarithm. So we're going to take the log or apply log to both sides. And if you want to use natural logarithm, you can. You get the same answer. So I'm going to do the log of 2 equals the log of 1.027 to the t power. My exponent, or excuse me, logarithm laws, properties tell me I can bring that t out front as a product times log of 1.027 equals the log of 2. And now I'll just divide by the log of 1.027 to both sides. And when you divide, again, calculator-wise, log of 2, make sure you close the logarithm on the 2 before you throw in the division, or get the decimal for it and divide that answer however you choose to operate your calculator. But those are 2 separate logarithms. You can't combine them. Log of 2 divided by the log of 1.027 gives the value 26.0172. This time is in years. So depending on what it asks you for, it takes about 26 years for your investment at this bank account growing at that rate to double. Again, it doesn't really matter how much you started with, $100, $500, $7,000. If it's growing at that rate, it would take about 26 years for it to double. And that's your answer for doubling time for this one. Okay. Let's look at another one. How long will it take a population to double if it is, sorry about that, growing continuously, so we're going to use E, at 20% per year? Okay. So for this one, we'll use an exponential function that has an E in it. So again, Q or P, it doesn't really matter. But population is initial population times E. See, continuous growth of 20%, we'll use a K value of 0.20. So E to the 0.2 T, or 0.20, same number. That indicates 20% continuous growth. If it were decay, we'd make the exponent negative, but it's not, so we make sure we make the K value positive since it's growth. You can just pull in some of those previously used skills. And if I want to double, again, it doesn't matter what the initial population is, because if it's growing continuously at 20%, it'll take the same amount of time. I want to double my initial population equals my initial population, E to the 0.2 T. The initial population variable cancels to 1. And you have 2 equals E to the 0.2 T. So you have an equation where the variable lives in the exponent that you're trying to solve for. The base is E, so we can apply a natural log to both sides. And it would really benefit you to use natural log here so that we can cancel out and get away the E. So if I do natural log of 2, that equals natural log of e to the 0.2t. Again, pulling from our beautiful logarithm properties, says that we can bring that 0.2t down. The natural log of e ends up being 1. We have the natural log of 2 equals 0.2 times t. We'll divide both sides by 0.2 because the t is what we're solving for. And if you take the natural log of 2, again, close the parenthesis on that natural log function so it stops after 2, or get an answer for that and then divide that answer by 0.2. And you get, the time is about 4657, and it's in years, right, per year. So ballpark, it would take about 3.5 years for the population to double if it's grown at this rate. Again, you have to pay attention to what you're asked to round to for the particular problem, but ballparking it would take about 3.5 years. So like a little under 3.5 years, but it would take about 3.5 years for population growing continuously at this rate to double. Okay, and again, the doubling, times it by 2, solve for time, you're good to go. All right, so next I have a couple of half ones. So here is one that asks you to find the half-life of Einsteinium-123, which is clearly a substance, and it decays at a rate of 3.406% per day. So we want to find how many, it'll be in days, because our time is in days, how many days, regardless of the amount of Einsteinium-123 you start with, how long will it take for half of that substance to be gone? Okay, so it's not continuous. It just says decays at a rate of 3.406. So that's 0.03406 as a decimal, in decimal form. Remember, you just divide it by 100, move the decimal place left twice, keep all the decimals, don't round yet. And because it's not continuous, we're just going to use our regular exponential, or if you want to use the q with an initial value times a factor to a power. It's the same formula, but you have to be able to pull and put the correct decay rate, because if it's decaying at a rate of 3.406%, you can't just put the 0.03406 as your B value. You have to be able to convert the 0.03406 to a B value for our decay rate. And remember, doing that, you find the decimal form of the percent and do 1 minus 0.03406. So that gives us 0.96594. I'm not going to round any of this because then it would not be exact. So that's your decay factor, B, that's going to go into our formula to find half-life. So we have some initial value times 0.96594 to the t power. We're trying to find half-life. So instead of, previous examples, we did double. We doubled, so we did 2 times the initial value. This time we're going to do half of the initial value equals initial value times our decay factor to the t power. Okay? Get rid of that. And same thing happens though. You still have that initial value variable divides to 1, and you have the 1/2 equals your decay factor 0.96594 to the t power, and now we're set to solve for t. And we have a base with an exponent equals a number, so, and it's a not e base, so you are welcome to just apply a logarithm here, or natural log, your choice. So that will take the log of 1/2 equals the log of 0.96594 to the t power. And again, we can take that t exponent, bring it out front as a product, t times the log of 0.96594 equals the log of 1/2. I mean, you could split apart the log of 1/2 if you're trying to be equal, but you don't You're trying to be exact, but I don't think this is one where you have to be exact. So we'll divide both sides by the log of 0.96594 in that order. Cancels it out on the right. And if you take the log, again, our natural log, but just make sure you're consistent. The log of a half divided by the log of 0.96594, you get 20.00219, and this was in days. So it takes about 20 days for Einsteinium 123 to be half of what it was that you started with. So that's the half-life of this substance, element, whatever you would like to label it for this problem. But it takes the half-life, again, it's the amount of time it takes to get to half of what you started with, regardless of the amount that you start with. Found the half-life, 20 days. There you go. Okay. Last example, another half-life question, but I wanted to do one with continuous rate, just so we covered all the bases here. So just a random radioactive substance, doesn't really matter for this problem because it doesn't specify, but we know that it decays at a continuous rate of 11% per minute. So to find the half-life, it's going to be the amount of minutes that it takes for half of that radioactive substance to exist because it decays. So the fact that it's continuous is going to use E. The 11% per minute is going to use a K value of positive 0.11. You know, change 11% to a decimal, divide it by 100. But the fact that, nope, just kidding, it is not positive. The K value is going to be negative because it is decay. So negative 0.11. Apologies there. So our formula, P or Q, pick your letter, is some initial value times e to the negative 0.11 t power. That's our initial setup. If we're trying to do, again, half-life, I swear that says half. If we're trying to do half-life, then we want to know half of that initial value equals some initial value times e to the negative 0.11 t. The initial value variables divide to 1. You're left with 1/2 equals e to the negative 0.11 t. So we have a base with an exponent. That's where our variable lives. It equals another number. We can apply logarithms, but because we have a base of e, I'm going to use and apply natural log to both sides. So we have natural log of 1/2 equals natural log of e to the negative 0.11 t. And again, because you don't really need parentheses there. Because you have the natural log of e to a power, the power can hop down front, be multiplied as a product. Natural log of e is just 1. You're left with negative 0.11 t on the right-hand side. You have natural log of half on the left-hand side. And then if you divide both sides by negative 0.11, you get the natural log of half by negative 0.11. You get a t-value of 6.3013. This was in minutes, so it's a little over 6 minutes. So I'll say 6.3. Again, just pay attention to what the question asks you around to for assessment purposes. So the half-life of some random radioactive substance that decayed continuously at 11% per minute, it'll take about 6.3 minutes for half of that substance to be there. All right, so there's half-life, doubling and half-life. Set up your equation, find your time, you're good to go.